Inside the combustion chamber of a modern jet engine, components are subjected to thousands of degrees of continuous heat and immense rotational force. It is an environment designed to push engineering to its absolute limit, exposing a core vulnerability in our construction materials. Standard iron and plain steel simply cannot survive here. Under these physical extremes, conventional metals face three fatal outcomes. They melt from the sheer thermal load, they fracture from the intense mechanical stress, or they rust away from rapid environmental exposure. To push aviation and heavy industry forward, engineers required a class of supermaterials capable of withstanding these destructive forces. The chemical antidotes to all three of these structural failures are entirely contained within one specific narrow column of the periodic table. The performance of our most durable machines is built into the subatomic architecture of Group 6, providing a level of resilience that mass alone cannot achieve. To understand how these metals survive where others fail, we have to scale down past the visible surface and look at the atomic mechanics. Group 6 elements share exactly 6 valence electrons. These interlock, pulling atoms into a tightly packed grid. Capable of multiple oxidation states, their bonds shift into stable configurations without snapping. This flexible architecture deflects extreme heat and corrosion, maintaining shape where conventional materials shatter. This descending column charts the transition metals of Group 6, which share a reputation for being hard, dense, and silvery white. At the top is chromium, atomic number 24. Think of this as the surface shield of the group. It is highly resistant to surface wear, making it the essential ingredient for producing commercial stainless steel. Moving one step heavier brings us to molybdenum, atomic number 42, the internal muscle. Engineers inject molybdenum into steel alloys to provide high-strength structural integrity for heavy manufacturing and construction. Descending further, we hit tungsten, atomic number 74. This is the ultimate heat sink. Tungsten possesses the highest melting point of all known metals, making it vital for filament wire and industrial tools that operate at extreme temperatures. At the very bottom of the column sits the heaviest element, seaborgium, atomic number 106. You won't find seaborgium in an engine block. This synthetic, highly radioactive element exists for only a fraction of a second before completely decaying. Moving down this sixth column represents a staircase of escalating physical extremes, peaking at tungsten's absolute heat resistance before collapsing into seaborgium's nuclear instability. To apply these elements in the real world, we rely on the science of metallurgy and the creation of alloys. We do not forge bridges or cast turbine blades out of pure tungsten or pure molybdenum. Instead, Group 6 metals function as vital additives. Injecting even a small percentage of these elements into standard steel provides the specific heat and corrosion resistance necessary for specialized industrial work. The end products of this alloying process give us the specialized superalloys and heavy armor plating used by modern militaries and aerospace engineers. Our ability to conquer extreme environments, survive immense pressure, and harness intense heat relies entirely upon our mastery of the microscopic behavior of Group 6's valence electrons.